Hello, I'm Unik. I will be solving educational code first round and explaining what I'm doing. Problem A. We have two towers of blocks of red and blue color. We can choose a tower with at least two blocks and move its top block to the top of the other tower. So we cannot make the towers empty. The pair of towers is beautiful if no pair of touching blocks has the same color. We have to check if it is possible to perform any number of operations to make them beautiful. Okay, so basically we have two stacks and we can take the topmost element from one stack and pop it from that stack and push it on the other stack. So if we imagine, like, here are two stacks, S1, S2, we can take the topmost element and move it to the other stack. We can imagine that those two stacks are actually located as follows. So this is S1, this is S2, and S1 grows from left to right and S2 grows from right to left. Then the operation of moving the topmost element from S2 to S1, it just moves where the border between those two stacks are. So before the operation it is here and then we move it here. But like the concatenation of those two stacks will stay the same. So we can imagine it as follows. Like we have this concatenation of two stacks. Like we glue their tops and then we can split in any place to get actual two stacks. And after that we want to make sure that in both stacks neighboring elements are of different colors. So in the concatenated string there can be only one place where neighboring positions are of the same color and we have to make the split there. So to solve the problem we will read two strings, reverse one of them, in which order they are given, from bottom to the top. So the last position is the top one and I want to merge, like I want the last positions to be also neighbors. So I will reverse the second string and concatenate the two. And after that we should check if there is at most one pair of neighboring characters that are equal. If it is true then the answer is yes, otherwise it is no. Because if there are more than one pair, like in each such pair we have to make the split, but we can make only one split. You can see, like in the last sample, before the concatenation there is only one such pair, but after we concatenate them there will be like the pair of these two R's also will be bad. I actually want to use strings, so I would like to use scene and cout. The input is not very big, so I don't actually like have to write magic strings to make input fast, but it is a good practice to write them anyways if you use scene cout. So we read the input, reverse the second string, concatenate it with the first one, and then count the number of positions. In which two neighboring elements are equal, and if it is at most 1, I will print yes, otherwise no. I want to say that like this idea of having two stacks is used somewhere, but it's not the same. They are glued in the opposite way, but yeah, in general, like there is this idea of implementing a queue using two stacks. So we will have two stacks, and so basically we have an array, and we want to do kind of two pointers, right? We can add element to the front and pop element from the back. So queue. Well, in queue it's the opposite, right? We can do push back and pop front, but that's just like depends on where you define front and back. So there are two pointers, and we can move both pointers only to the right, and when we move the right border to the right, we have to add this element like here, and when we move left border to the right, we have to remove the last element. And so we can implement that using two stacks. We kind of imagine that we split our segment at some point, at this point, and we store the elements to the left of that border in the first stack, and like the leftmost on the top, and we store the elements that are on the right in the second stack, and the last one is on the top, actually. So those two stacks are glued together like by the bases. Why is that? Well, because in stack we can only access the topmost element, and we want to be able to access like this front and this back. So we want to be able to access this element and this element in the queue. Well, we don't need like full access, but we do need to be able to pop this element and push like new elements here. So using toStack allows us to do that, except in one situation, when we want to pop the element but this stack is empty. So like this border will not move during our algorithm. We move the pointers, we push pop something, but this border in the original array will stay in the same position, and at some point left border will reach this place, and at later point we will want to move it, but at that point like this stack is empty, and this stack has some elements. So to pop element, we want to pop it from this first stack, but we can't, it's empty. So we kind of need to pop this element, but it is inaccessible because it's just text. So what will we do is we will just take this whole thing, pop elements one by one, remove the last one, and then push them back, but not in the second stack, but in the first stack. So like at this point, our elements, like we store this segment of the array, and our border is on the left border that splits two stacks, and we want to instead make it to be on the right. So we will pop elements one by one, and each time we pop an element we will push it to the first stack instead. After we completely clear the second stack, all the elements will be in the first stack and they will be in reversed order, so they're still like in the correct order like we wanted, but they're now in the first stack, and we can just pop the elements, like we continue doing the same. Further. So this looks like it's slow, right? We do linear number of iterations, but actually each element can be pushed only once to the second stack, and then only once to the first stack, and then it will be popped from the first stack. So with each element we do a constant number of iterations. So the total working time is amortized linear. Like, why would we want to do that? Like we have Q in standard library. We even have DAC. But like the thing about using simpler data structures to implement harder data structures is that if we are able to maintain something additional for the simpler data structures, we can probably do it for the harder data structures too. So using this technique, which is, I think it's called like Q on two stacks, we can implement what is called Q with minimum. So it's a data structure that allows like queue-like changes, like push back and pop front, and also maintains minimum of the elements, or like maximum. Or basically, it can maintain well, anything that can be, I guess, like any associative operation. And I think that even like commutative is not necessary. Yeah, I think we can do Q with matrix multiplication or something like that. So yeah, we need associativity, so we can change like the order of execution of operations, but we don't need committed duty. How would we do that? Well, we start with implementing stack with minimum. So we need to be able to push back, pop back, and get min. But that's kind of easy. Just maintain another stack in which you write minimums, and so like when you do push back some new element, you will recalculate new minimum and push it to the stack of minimums. It will be just minimum of everything that was in the stack before and the new element. And when you do pop element, you need to pop the corresponding minimum. And get min is just like take the highest element of the stack. So now we have this stack with minimum, and we can implement queue on two stacks, just using like push back, pop back, and be able to maintain get min. So how do we implement queue with minimum now? We implement queue with two stacks which maintain minimum. Now when we want to take minimum from the queue, we just take minimums from both stacks and return minimum of them. So get min is constant, and push back and pop front are amortized constant, linear in total. And like that's a nice data structure, which it is actually used in competitive programming. There are problems that use this. Basically, if you need to do two pointers and maintain minimum in this window, it's queue is minimum. So that was problem A. Okay, problem B. We have segments on the line. F of x is a number of segments covering point x. Integer point x is ideal if it belongs to more segments than any other integer point. So f of x is the strict maximum. Like it is strictly bigger than all other values of f in all other points. We are given point k. Want to determine whether it is possible to remove some segments so that given point k becomes ideal. Remove. So it is kind of stupid to leave segments that do not contain given point, because like removal of that segment can only decrease value of f in some other points. So removal of that segment is always a good operation. So so it makes sense to only leave segments that cover our given point, and then doesn't make sense to remove any of those, because like removal of such segment decreases f in our point by 1 and maybe in some other points, but that just means that like relative to f for our point, it can increase f in some points that are not covered by the segment by 1. So we just look only at segments that contain point k, and well, basically we need to check if there is any other point that is covered by all of them. We can just like count find their intersection and check if it only contains point k or not. I think this is simpler than problem A, but I don't understand the difference in difficulty between cakewalk problems, so okay, so how do we find intersection? Intersection is always a segment. Well, it can be like a line or array, but we can just say that line is a segment from minus infinity to infinity, and then like we take maximums of left borders and minimums of the right borders. That will be the left and right border of the new segment of intersection. And well, technically I should say that left and right borders are minus infinity and plus infinity, but we can just say that they're equal to k minus 1 and k plus 1, because we only care if they're actually equal to k or smaller for left border and bigger for right border. Actually, we can just check if like there should exist a segment that has left border equal to k, and right and exist a segment that has right border equal to k. So we can even say like simpler. Just maintain two flags, which we can maintain in one mask. And if both flags are true, then the answer is yes, otherwise it's no. Problem C. Have n sorts of tea and n tasters. For each sort of tea we know the volume of that sort of tea, it's AI, and for each taster we know how much can they drink. Tasting will be conducted in steps. In the first step, the is taster tastes the is sort of tea and just drinks as much as they can. So like minimum of the volume of that sort of tea and how much he can drink. And then AI is decreased by that. Only AI decreased. Like BI is not decreased, right? Then they move to the next sort of tea. So like, oh, it's not even cyclic shift. The first person and the taste. All right. And what do we want to find? We want to find for each taster how many they will drink. Okay. So for each sort of t, for each sort of t, tasters with indices I plus 1 and so on up to n will drink it in this order. So we want to find out what will be the last taster that drinks at least something of this particular tea. We can do it with binary search, like we can binary search this last person and check that the sum of values b from the ice taster to this one is at most the volume of this tea or not. For that we can recalculate prefix sums on array B. And so we will find the only taster that will drink less than what they can, but greater than 0. So for some segment of tasters, they will drink just as much as they can. For one, they will drink something, and we can find that number. And for all others, they will drink just 0 of that type of tea. And we want to, remember that information. So for a segment of tasters, we kind of do like +1 for them, which means that one more time we need to add their bi to their answer. And also for one taster we should just add some value to their answer. So adding just one value to the answer is easy, and +1 on segment of line, we just need to calculate it afterwards, is done with, again, prefix sums. Like we will do +1 in the beginning, -1 after end, and then we will run left to right and calculate prefix sums. And like for all the tasters that are on that segment, we will add +1, and for all others we will not. That's the solution. I'm not sure if it's the simplest one, probably not, but it's simple enough for me at least. Okay, so we need to calculate prefix sums on array B. Done. We also have array for answers and array on which we will do this like +1 in the beginning and -1 in the end, and then calculate prefix sums. And we need to clear them between tests. Okay, so now for every sort of team, we want to find with binary search the well, for example, we want to find the first such person, so the sum of B from i's person to this one is at least AI. That would mean that prefix sum before this person minus prefix sum in I is at least AI. We can rewrite it as prefix sum in R is at least AI plus prefix sum in I. And we want to find the first such place, so this is done with lower bound. We know that prefix sums are non-decreasing because all the values are non-negative, and then when we calculate prefix sums will be non-decreasing. So we want to find the first prefix sum, which is at least AI plus pref I. It can be n, which will mean that no prefix sum is good enough. No, actually, wait. We have n plus 1 prefix sums, so yeah. N means that up to the last one is big enough. N plus 1 would mean that there is like no prefix sum is big enough. So if R is equal to n plus 1, we should just say that everyone starting from taster number I will drink this tea to their full capacity. Otherwise, everyone starting from ice taster and up to the R minus 1 y 1 will drink to full capacity, and this one will additionally drink AI minus sum of capacities of all the previous guys. Then we calculate the prefix sums. And now for the East taster, we should say that they drink their full capacity Ci times. So we add this product to the answer. Problem D. Have an undirected graph and vertices and edges and is divisible by 6. Yeah, sure. Each edge has a weight. Graph has the following structure. Okay, so it is just n divided by 3 triangles, which are disconnected. You have to paint the vertices into 2 colors, red and blue. Each vertex should have 1 color, and they're split. So half of the vertices should be red and the other half is blue. The coloring is valid if it meets the constraints. The weight of the coloring is the sum of weights of edges connecting 2 vertices with different colors. This is maximum possible. Calculate the number of colorings with this weight. Printed model. Okay, so in each triangle there will be at least 2 vertices of the same color. The edge between them is not added to the answer, and the other 2 are added if the third vertex is of different color. So in each triangle we can either choose 2 values to add to the answer or not choose anything. All the weights are strictly positive, so to get max weight we would like to take just 2 maximums from each triangle. We can always do that. In the half of triangles we will have 2 red and 1 blue vertex, and in the other half 2 blue vertices and 1 red. So we have to have this structure. So in each triangle we have to take 2 maximum values, but 2 maximum values can be not unique. And so okay, so the structure of the coloring can be like split into 2 independent parts. First, in each triangle we want to choose 1 vertex that will be of unique color, and correspondingly we don't choose the edge not connected to this vertex. And that edge should be one of the minimums, because we want 2 maximums. And then, after we made this choice for each triangle, we choose which of them will be blue and which are red, and that should be just like half a blue and the other half a red, and it's absolutely independent of everything else. So that's just like multiply the number of ways to choose these unique vertices by choose n over 6 from n over 3. And then like for each triangle we need to just multiply the number of ways to choose one edge that we will not take, so it's the number of minimums. That's very simple combinatorics. Well, actually, let's divide this way. So let's choose n over 2. And now, n times we need to read 3 values and calculate how many of them are minimums. You are playing yet another game where you kill monsters using magic spells. Yep, there were a lot of similar problems recently. And cells. This monster is in cell number I with HI health. Basic spell deals 1 damage to the chosen monster for 1 mana point. Okay, cool. Also, you have a special scroll with explosion spell that you can use only once. You want to finish killing monsters with explosion. So first we will cast the basic spell several times and then the explosion to finish it. How does explosion work? First you choose the power of the spell. For X mana points, deal X damage. Then we choose some monster I, which will be targeted. So if its current health is greater than X, that's not good because we want to kill all of them, right? The minimum total MP, you need to kill all the monsters. So this is just a bad option. The explosion should be the last thing we do. So we do not want to do that. If HI is at most X, the ice monster dies with an explosion that deals his HP -1 damage to the monsters in the neighboring cells, if they exist and still alive. So like they will be away from some point with always decreasing the secondary explosions, they do not have the power X -1, they have the power, the health of the first one -1. Okay, so like from the one we start with, the health should strictly decrease in both directions to kill everyone. Monsters don't move between cells. Okay, so we are given some towers. We can decrease some of them first. And then we will choose one tower and then from it all the others should be strictly decreasing until we reach zeros. So like if we just fix this middle one, can we calculate the optimal answer? So the mana we will use is sum of all decreases plus the resulting height of this main one. So on the main one we will spend its initial height in any case, so it doesn't make sense to reduce it before explosion, because like we want to get this decreasing part, so this one should be as high as possible initially. And then like from this fixed tower we should just greedily go and choose the highest possible value for each next tower, which is strictly less than the previous one, and at most its initial height. And like these heights we will remove for free, so we want to maximize their sum basically. Okay, so like, the solution in n² time is simple, just like try all the options for the main tower and greedily like run to the left and run to the right. And calculate the sum of these things. The heights are pretty big. Not like interesting why they're not 10 to the 9th. Like the answer is at most just some of them. So it's not because long will overflow. Interesting. Well, okay. I guess we just want to like calculate the scores and like for all starting positions and then choose the best one. And calculating the scores running to the left and to the right is the same, and they're independent. So we will just focus on running to the left. So okay, each time we move to the left, the new height will be either the previous height -1 or if like it was lower initially, just initial height. But when we like, do this jump to initial height, everything that is happening next will not depend on where we start. And actually, like the sums of everything that will be next to the left, it's just answer for this tower on the left. Like basically, we start from its height and run to the left. And before that happens first time, we just decreasing by 1. So if we are able to find this position, then we just need to like take answer from it and add some like arithmetic sum of arithmetic sequence. Okay, that sounds easy enough. Like, we want to find the closest element on the left so that its height is smaller than our height minus distance between them. So AJ is smaller than AI minus distance, but distance is just I minus J, since we know that J is smaller than I. And we can move J here and we'll get AJ minus J smaller than AI minus I. So we can just like maintain stack of basically in array with these values we want to find like closest less element on the left. That's standard problem with like scanline with stack. We'll maintain stack of like increasing values, and when we insert the new one we remove everything that is greater or equal and find the first smaller, and also maintain the stack. That's just standard problem. Okay. So I will like literally solve the same problem to the left and to the right. I can just reverse the array and run the same solution. But I need to be careful to like remember to reverse answers and store the first answers. So the first answers will be stored in the array B. So I'm calling solve. Solve 2, I guess. Then I need to store the answers, then reverse the array, then again call solve2, reverse the answers, add to BI, and what we actually want, we want maximum of those values, and to get the actual answer to the problem we need to subtract it from the sum. So need to calculate the sum and find the maximum of values. So I didn't reverse A back, reversed it to like before the second solve, didn't reverse it back, only reversed the answers, but that doesn't change the sum, and I don't actually need to know AI to calculate like, its answer, so it's all good. Sum minus maximum answer. Solve 2. For each position, we want to calculate the sum of like those decreasing sequence, and I want to maintain strictly increasing stack of values ai minus I and maintain answers. So my new value is ai minus I. The value on top of the stack, like in the stack I will actually store the position, because I need to know the position. And if my value is at most a on top of the stack minus its index, then I should remove this element from the stack. Now I need to calculate the answer. So if the stack is empty, we kind of well, we're just saying that all will be good. I guess we can say that we have -1 initially, and then yeah, okay. Well, I still need to do if, but it's better in list in this regard. So answer for me is sum of arithmetic progression so the I start with ai, then ai minus 1, and so on. I arrive at ai minus the distance, but both ends should be not included. But I can just say, okay, let's give ends to the function that will calculate the sum, and it will reduce them there. And if I arrived somewhere, I should add to my answer the answer for that position plus the height of the tower in that position. And add myself to the stack. So I want to calculate the sum of all numbers from L to R, both not included. That is not correct. Sum is 18, so it didn't find anything. That's insane. is 0. How is that possible? um, I guess I set negative values here, but that also shouldn't be possible, because this value should be greater than a here. Oh, but this can be x minus 1. Okay. So, yeah, that helps. Okay. Problem F, we have 3 on n vertices, k chips. In distant vertices, they are colored black, the remaining vertices are white. So we iterate over all chips in cyclic order. We take a chip, move its current vertex to an adjacent white vertex and make it black. What is the maximum number of moves you can perform? So okay, assume we did binary search and answer. So for each chip we know how many moves using that chip we can make. So we should choose a pass with given start. We cannot go back because that vertex is black. So we have to choose non-intersecting path with given starts. I feel like we should be able to do some dynamic programming on subtrees. So if we did binary search, here's subtree, its root, it has the only edge that goes outside, so only one pass can use this edge. This pass can either start inside or start outside, or there can be no such pass. But in any way, there will be at most one pass that uses this edge. So all the other paths do not cross this edge. It means that if they start inside the subtree, they stay there. If they start outside the subtree, they never go to the subtree. So for this subtree, well, let's say that for simplicity right now we just fix which of three possibilities for this edge happening. Like either it is not used, it is used by some path that starts in the subtree, or it is used by some path that starts outside the subtree. Then what we want? Well, if it is not used, then we just want to lay the paths that start inside the subtree. We just want to check if it is possible. If it like the path goes from the subtree to outside world, what do we want? Like we know that it will go through this edge and then some, probably, and well, that sum should be as small as possible, right? So we want to understand for what smallest length of like this part we can do that. And if the path crosses in this subtree from the outside world, like the opposite, it arrives here, and we kind of like want to understand what is the longest tail we can accommodate. Like, let's say that something arrives from outside world. What is the longest thing we can accommodate? And actually, we can see that those three possibilities, they can be stored in the same manner, basically. We kind of just want to store this maximum length of tail that we can accommodate, but it can be negative or zero. Zero means that we cannot accommodate anything. Like you can't even use the root of our subtree if we arrive from outside. That just means that nobody will use this edge. If it is negative, then it means that actually one of our paths have to go outside and use like minus our GP value number of vertices outside. So if it is -1, it has to use this edge and this vertex respectively, and then stop. If it is -2, it has to use one more edge and then stop, and so on. So we want to calculate this GP, GP of subtree. What is the maximum length of tail we can accommodate? Okay, so now how do we calculate it? So let's say that we have calculated it for all our sums. If we have at least two sums that has to go outside, so use this root, then it's impossible. If we have one such sum, then let's say that it is this one. Yeah, let's start with easier case when we have no such children. There's also a case when we have to start some paths here. Well, it is similar to just saying that we have additional sum that has to use this vertex and then sum. right? Yeah. So yeah, it's just similar to adding new sun with dp value equal to minus length of the path that should start here in vertices. So if we have to make 0 moves, the corresponding dp value should be -1 because we still use the root. Okay, so now if we have at least 2 negative values, it's all bad. If all the values are non-negative, that means that we surely can accommodate at least somebody that comes from outside, like at least in the root, and then we can choose one of the suns and continue there. So our dp value will be maximum of dp values in children plus 1. And if we have one negative value, and some non-negative values. Okay, among non-negative values, we just care about the maximum one, like how much we can accommodate in the best case. And here, like we start the path from here, we go to the root in our subtree, and we can either just go outside or go to the deepest sun, in the sense like if it can accommodate our tail, then we don't have to use this edge and then the dp value is 0. Otherwise we have to go outside, and thus the dp value will be what? This dp value plus 1 because we spend one move. That's it. So we, to summarize, do binary search and answer, then calculate this dp. We root the tree anywhere. Calculate this dp, and to recalculate, we need to like consider several cases. I guess we will like maintain minimum dp value, maximum dp value. If we encounter a negative value and minimum is already negative, then it's just bad. We can either just stop everything or just say that the dp value here is -infinity, and yeah, we will get something negative in the root as a result. Otherwise, if that didn't happen, we just check if the negative value is, well, the minimum value is negative or not. If it is not, then our dp value is maximum plus 1. And if it is negative, then we compare, like, can the negative, like the path that goes outside that sun, use the maximum of the suns. If it can, then our dp value is 0, otherwise it's minimum plus 1. So the structure of our solution is binary search and calculating DP on the tree inside. DP on tree is usually DFS, and DFS is a slow algorithm. Probably because of recursion, or I don't know, for some other reasons, but yeah, DFS is kind of slow. And well, I'm sure that it is not needed in this problem, but like for educational purposes, when you do DFS on the same tree from the same root many times, for example, when you do binary search and answer and then calculate something in DFS, it makes sense to do DFS once and then like store how do you do DFS, which is like it is nicely done by renumerating vertices in DFS order, and for each vertex we will just we will have the vector of sons, and for each vertex we will have a parent, maybe. I guess it's not even needed. And then after we did that, instead of doing DFS each time, we will just traverse vertices from the largest to the smallest and calculate DP. We have a vector of sons, and we know that all of them had bigger numbers, so DP for them is already calculated. So this doesn't require recursion, and thus it's much faster. This thing can optimize the code like 10 times for sure. So we will need like 2 graphs because we need to store the initial tree to do the first DFS, but then we also need to store the vector of sons. Some cleanup. DFS. Let's say it will return new ID of this vertex. So we're trying to go everywhere except our parent. So our new ID will be m, and then we increase m. And for should be here, and for this vertex with this ID, we need to say that it has another sun. That is the new ID of vertex u, and return ID here. Okay, so we renumerated the tree. So the root is 0, and for every vertex, all the suns are on the right. We can check. Okay, I guess I need to remember IDs because I have the list of vertices. I didn't want to do that, but I guess it is required. So we are given vertex v, but the ID of that vertex is actually stored in ID of v. So we remember that this is the is vertex of the given ones. And now do binary search. 0 is good for sure, and well, n plus 1 is bad for sure. Actually, like n minus k plus 1 is bad for sure, but let's not play that game. So if it is good, then update L, otherwise update R, and we can play this number of moves. That sounds right. Maximum number of moves we can perform. Okay. So let's in array B we will say that -1 if it is not a start of any path, and otherwise the length of the path we should traverse from this vertex, which is d divided by k plus 1 for some prefix, and that prefix is of length d mod k. So if I is strictly smaller than d mod k, then we should add 1. Okay, and now we just calculate the dp by traversing our vertices in the decreasing order of ID. So need to calculate what is it? Need to calculate minimum and maximum values, and we start by saying that they're both zeros, but if there should be a path starting in this vertex, then both of them are actually minus this length plus 1. Yeah, we use this vertex surely. So like if there was the sun with like corresponding DP value, that corresponding DP value should be one more. Now we iterate over the suns. If dp of u is negative and L is also negative, that means that there should be two paths that both contains vertex v, which is bad. Well, I mean, in this case, big N is infinity because, well, it is bigger than every possible dp value. So, yeah. And then update minimum and max. Alright, so if not bad, then if minimum is negative, then it can either like go to the biggest sum. So what happens here? Like minus L is the number of vertices we need to use, and R is R is again number of vertices in that sun that we can use. So if minus L is at most R plus 1, because in that sun we can use R vertices and plus 1 for the root for the vertex v, then dp of v is 0. Otherwise, dp of v is L plus 1 minus L minus 1. Why is that? Because like this long path doesn't fit in the largest space we can give in the sun, so it has to go up, but we have spanned one vertex here, so yeah. And here it's just R plus 1. We had R, and we can also afford this root. When we calculated all of that, we now know the dp value for the root, and it cannot go outside, so it is good if dp for root is non-negative. If it has to go outside, so it's negative, it's bad. Otherwise, it's good. Well, that's insane. Okay, let's see what is the graph that we have built. So the graph is correct. Yeah, this is also correct. So here dp should be 1. Okay, let's just print the dp values. One should be 2. 0, 0. Oh, 1, 2, minus 3, minus 2, minus 1. Still minus 1. What? Oh no, that's right. 0 because it can go down. Yeah, that sounds right. And they have 23 minutes, assuming that f passes. Cool. Problem G. Simple undirected graph. Vertices have values. Value AI are non-negative up to n-1. We'll be removing vertices. We're allowed to remove vertex I only if its degree is equal to AI, like at the moment, right? When the vertex is removed, all edges also removed, thus decreasing the degree of adjacent vertices. Valid sequence is permutation, like in which order we remove the vertices. A pair of vertices is nice if we can remove them in any relative order. Right? Count the number of nice pairs of vertices. Additional constraint on input: there always exists at least one valid sequence of removals. Okay, so F is accepted. There always exists at least one valid sequence of removals. Isn't it like totally greedy? We can remove vertex if and only if the degree is exactly equal to the number. So while the degree is greater, we cannot remove it. When the degree becomes equal, when the degree becomes equal to AI, we cannot remove it decrease it further. So we have to remove this vertex before any other of its neighbors are removed. But then I want to say that the removal of this vertex only matters for the neighbors of that vertex. So we can remove it right now. It is a valid action, always. So like, to find some order of removals, we just do each action as soon as it is allowed, and break ties in some way. And like, breaking ties is the place like how it can be possible that for two vertices we do not know whether we will remove one before the other, and like it can create a chain reaction. So let's say that we have a chain reaction, and we can remove all of these vertices when their degree is exactly 1, and this vertex when it's 0, and we have additional vertex that we can remove when its degree is 0 and it is not connected to anything. Then in the beginning we can only remove this vertex and this vertex. When we remove this one, the degree of this vertex becomes equal to 1. So basically we remove this chain left to right, and we can insert this vertex anywhere in that order. Well, it feels like we should be just able to say that, like, for each edge we know which vertex we remove before which one. And I want to say that there are no other constraints. Why is it true for each that for each edge we know which one we remove first? Well, it's kind of like by induction, I think. Like, let's look at the one valid order that we found. It assigns directions for all edges. Now I want to say that there aren't any valid orders that flip the direction of any edge, because like there are no cycles, and that means that flipping the direction always, like, basically the the number of outgoing edges for each vertex should be equal to this number. So basically, we are given just we are given a graph. For each vertex there is a number, and that number is outgoing degree. We need to arrange the edges so that it is a duck and all the outgoing degrees are correct. And I want to say that, like, there is only one way to do it, maybe zero, but if we like 0 or 1. Why is that? Because, like, if we found a way, suppose there is other way, find the leftmost vertex in the topological ordering for our initial orientation of edges. This vertex can only, like, we can only flip edges to the right, but all of them are directed from it. So if we flip some of them, non-zero, non-empty subset of them, we will decrease strictly outgoing degree of this vertex. That's bad. Okay, so now we have directed the edges. So now the problem is as follows. Like, we have directed graph. We need to calculate the number of pairs of vertices so that their relative order in topological ordering is not fixed. The order is fixed only if one vertex is reachable from the other. We can find which vertices are reachable with bit sets in of nm divided by 64. And well, that's it. I should be able to implement that in 30 minutes. But well, no, I'll have to talk less, I guess. Okay, yeah, I guess that should be. Oh my god, test cases, really. So we found all the vertices from which we can start. Put them in the queue. Now in this order. Just remove them. Let's remember for each vertex its position in this queue. This queue is basically topological ordering. So why did I remember it? Because I want to only leave the vertex, the edges that go to the right. Well, I kind of just want to calculate, reorder like the graph basically. So now we have this graph. So instead of bit sets, we will just use unsigned longs and run the solution n over 64 times to not have quadratic memory. Okay, I'm not sure what type built-in pop count takes, so let's make sure that if it casts to signed long, it still should be fine. Let's check that it doesn't depend on the block size. almost in the limiter 2, which is not bad. Thanks for watching. It's an okay result, I would say. Goodbye.